So in this part of the experimental techniques lectures, I'm going to look at some of the ways that you can try and improve your measurements, either to measure signals faster than you otherwise be able to, or to get them with a lower noise level in them. So our starting point here is we're going to look So in this section of the experimental lectures videos, we're going to go on and look at ways of improving your measurements by using some particular techniques. So we're going to look at four things. So firstly, at doing stroboscopic measurements, and at phase-sensitive detection, null detection type techniques, and then pump probe. Okay, so our starting point is the Nyquist-Shannon theorem. So this says that if we have some frequency we want to measure at, then we need to sample our measurement at twice that in order to be able to get an accurate measurement of the signal we're interested in looking at. But doing measurements for very high frequencies is expensive at best, and can even be impossible to go and do. So resolving a fast signal might therefore seem like an impossible task. So here again is a time-varying signal, and the black dots represent how fast we have to do the measurements in order to satisfy the Nyquist-Shannon theorem. And that might, you think, may get to a point where it was going to be too difficult to go and do. So there are some tricks we can play. And a stroboscopic measurement allows us to, under some circumstances, reconstruct a very, very fast signal, even when we can't repeat the measurements. So it works best when you have a single sample that you can measure very, very quickly. So the time taken to do a measurement is quick. It's just the time taken to then repeat that measurement is slow. And also the timings of the measurement can be made very, very accurately. So in other words, there is a low level of jitter. There's if you say you want to measure something at a particular time, you can measure it at that time. You can measure it very, very quickly. And it also relies on a signal that is repeating itself. So here we have our same time-varying signal, but it's a repeating time-varying signal. And so the black lines each represent one period of that signal. And what we go and do is we go and sample it once per period, but at a slightly different time offset in each period. And then because we know exactly when we measured it, and because we know exactly how fast this signal is repeating itself, we can take those individual measurements and we can go and reconstruct it back into a signal. So this is the sort of technique that works if you can repeat your measurement over and over and over again and be fairly confident that each time you repeat it, it's going to look the same. And then we're able to go and take a snapshot at a short time after the measurement is happening. And after that, it's just a process of reconstructing the signal from the original data set. And so the actual measurement we take to reconstruct this signal might take many, many, many periods, depending on how accurately we wanted to go and do it. But you do end up reconstructing something which gets you much higher frequency signal than you'd be able to if you try just measuring it all in one go. So that's the basic idea of a stroboscopic technique, and we'll come back to that later on. But one of the important things that you need to get your heads around in thinking about doing measurements is to be able to switch between what's going on as a function of time and what's going on as a function of frequency. And so the relationship between time and frequency is all given by the Fourier transforms, which is a thing you'll have looked at in Maths 4 last year. And so what we're going to do now is I'm going to show you another class of measurement techniques we use called phase-sensitive detection, also called lock-in or AC techniques, which is a very, very powerful way to measure a small signal in the presence of a lot of noise. And this comes down to having a good understanding of what's going on in terms of the frequency of an environment and the frequency of the measurement you're trying to do. And so the general principle here is that you find a known frequency and phase in which to go and do the measurement. So this, for example, might be that you actually deliberately excite the measurement with an AC signal or modulate the signal at some well-known frequency. So for example, if it's an electrical measurement you're doing, you might supply it with an AC current at a certain frequency where you're controlling the frequency you're supplying to the measurement. If it's, say, an optics measurement, then what you might do is deliberately go and interrupt the light path in your optics experiment with a known frequency. And then what you go and do is you look at the signal you get back out of your measurement, specifically at that frequency and at that phase, and then you use that to average out all the other signals that are going on in your measurement. So we can have a little look at how that works with a graphic example, but how we actually do that in terms of the electronics. So the particular instrument that's used to go and do this is called a lock-in amplifier. And this is kind of a block diagram of how it actually works. So I'll talk you through the block diagram and then show you why this is working and why it's averaging out the signal. So we have our experiment and we have some kind of, in this case it's an electrical measurement, so we have a voltage source that's going at some kind of known frequency. And we're measuring some kind of resistance in this circuit. So we take the voltage drop across that resistor, and the first thing we do is we amplify it a little bit. And then what we end up doing is we also take the signal, the oscillating voltage signal, and we feed it into something called a phase-locked loop. What a phase-locked loop is going to do is it's going to produce a sine wave that's going exactly at the frequency that the input is being driven at. So in practical terms, if you're, say, driving your current source, your voltage source with a signal generator, you feed the signal generator into the phase-locked loop as well, so that it locks in and produces a sine wave that's exactly in the same frequency in the same phase as the signal generator is running at. So then what we do is we take that sine wave we've just generated, which is locked to the frequency we're interested in, and we multiply it with the voltage signal we're measuring. And then having done that, we then take that signal and we then average it over time, which is basically the same thing as having a low pass filter. And then finally, we amplify it all over again and look at the output. Now, why does this work? Well, okay, let's go and do this graphically to start with. So here is the signal we're trying to drive our measurement with, this blue oscillating sine wave. So we're producing that. It has a well-known frequency and a well-known phase because we're making it. And then we look at the signal that we get trying to measure, in this case, some kind of component that's responding to that sine wave. And you can see I've calculated a lot of noise onto this measurement. So you can also see there's a sine wave there, but there's also an awful lot of noise kicking around. So this is what we'd look at the point at which we've amplified our noisy signal a bit, and we've got a nice sine wave from our phase-locked loop. So we now multiply them together, and what we do is we get the green signal. And what you see happening is that every time that the response signal was going negative, then our drive signal, the blue line, was also negative. And so when you multiply them together, it flips over and becomes positive. And so what we end up with is a signal which is mainly going from 0 to some positive number. And if we then average that, then we get a nice steady signal that actually turns out to be related to the size of the voltage. Okay, so can we actually go and show? Okay, so what we have is we have our system being driven by some reference signal, which I'm just going to write down as sine omega naught t. And then we have a measurement we're carrying out. And in order to represent the measurement, I'm going to take it like a Fourier series. So it's just going to become a sum over different frequencies of V omega I sine omega I t plus some phase angle. Okay, so what we're going to do is going to follow what we did with the in the graphical explanation. We're going to multiply the signal we're measuring by our reference signal. So V measured times V reference is going to be equal to sine omega naught t times our sum v omega I sine omega I t plus phi I. And now we're going to go and split this sum into two parts. It's going to be one part which is going at the same frequency as our reference signal, and then some part which is going to be going at all the other frequencies. So we write this now as v omega naught sine squared omega naught t plus a sum for I for omega I not equal to omega naught v omega I sine omega naught t sine omega t plus omega I t plus phi I. Okay, so that's done the step of taking our signal and multiplying by the reference. And the next step we had to go and do in how the phase center detection works is we had to average it. So we're going to write the average, v measured, v reference, and that's going to be given by integrating v measured by v reference with respect to time, 0 to some time, and dividing by the integral with respect to time over the same time period. Okay, so the other thing we're going to go and do is remember that if we have sine A times sine B, that's given by a half cos A minus B minus a half cos A plus B. So as we're going to write down the integral, we can then also sort out these sine squared and these sine product two signs here. So this is telling you that sine squared A is equal to a half minus cos 2A. So we're going to write down here. So we're going to have the integral 0 to t, v omega naught constant. That's sine squared omega naught t, so that is going to be a half minus a half cos 2 omega naught t. And we can do that bit as one integral. And then the sum of integrals, we're going to have v omega I, and then this bit here, put the half there, we're going to have cos omega I t minus plus phase minus omega naught t times cos omega I t plus phi I plus omega naught t, and that's also respect to time, 0 to t, and that lot is also 0 to t dt. Now we don't actually need to evaluate many of these integrals, because if you stop and think about this, then if we integrate this over time, well, it's just a cosine function, and a cosine function oscillates plus and minus, so its integral over time must be approximately 0. Certainly if we integrate for a time t, which is much, much bigger than 2 omega naught t is equal to 2 pi, then this integral here must go to 0. So in fact, we can lose that term so long as we keep t big enough. So long as the t we're integrating to is such that omega naught t, 2 omega naught t is much, much bigger than 2 pi, then we can lose that integral. And actually the same is going to be true over here. So this integral is going to go to 0 in the same condition, as long as that we're integrating such that this omega naught t, this whole term here, is going to go, and we're going to look at lots and lots and lots of periods in our integral. This term is going to go to 0. This one's a little bit trickier, because it's the closer we get to the reference frequencies, the things we're interested in, the longer we have to integrate for, in order to be certain we're not going to have it included in that sum. But if we integrate for long enough, then that term goes to 0. And so the only thing that's actually left in this average over here becomes the integral of a half dt over the integral dt times the voltage omega naught, 0 to t, 0 to t, and fairly obviously that is just v omega naught over 2. And so what we've actually gone and done is by multiplying it by our reference signal and then averaging for a very long time, we've just got ourselves left with only the omega naught over v omega naught over 2, which is the signal we're actually interested in measuring. And so that's why what we get tells us exactly the signal we're trying to do, and it doesn't matter what other signals are going there, they all just cancel themselves out. Okay, so why is this a good thing? Why do we go about doing this? So in the noise lectures, we're going to look at what goes on in terms of the noise sources in a typical lab. So we can draw a picture of the noise sources by looking at the amplitude of the signal, V as a function of frequency, versus the frequency. And what we see is that a typical noise spectrum has some 1 over f noise, and it goes flat with white noise. And then what we expect to see is certain frequencies we get spikes of noise. So these might be, say, 50 hertz, 100 hertz, and then this could be higher frequencies, which might be to do with, say, Wi-Fi signals or phone signals and similar. So if we measure our system at DC, so down here, then what you can see is you're going to get a lot of intrinsic noise in your measurement because of all the 1 over f noise. So you might say, for example, measure averaging your signal for a certain length of time. Say you averaged for 1/10 of a second, then effectively what you're doing is you're measuring the signals in a region like that, where this would be 10 hertz. So we're measuring with a 10 hertz bandwidth because we're measuring for 0.1 of a second, but because we're measuring a region which has a lot of noise, we're picking up this much signal that we weren't interested in. And so we have quite a noisy background. And all we can go and do about that is try and average for longer and longer and longer to try and beat that noise down. If we're doing averaging for longer and longer and longer, what we're doing is we're effectively moving this bandwidth to smaller and smaller numbers. So rather than being a strip this wide, we look at a strip which is much, much smaller. What we do with phase sensitive detection is we say, okay, that's fine. Let's instead go and actually force our experiment to run at a certain frequency. We'll pick a certain frequency where we're outside the 1 over f noise, and ideally, and we're away from any other sort of noise sources. So let's say we're going to pick here to run our measurement at. So this is our omega naught. So we're forcing our experiment to run at this frequency, and it has some kind of response, which is this red signal here. So this is what we're trying to measure. And what we're effectively doing is saying, okay, let's just measure in this range, and let's go and measure just precisely at our omega naught. And what's controlling how precisely we're measuring at omega naught is how long we're going to average our signal for, because that tells us back in that expression for the when you calculated the effect of averaging, that was right at the end. There was that term which went as cos omega I t minus omega naught, and the longer you average for, then the closer omega I and omega naught can be, you can still average away that cosine term. So that's what's controlling how much we're actually measuring. So what we're going to do is going to do the same 10 Hertz bandwidth measurement. And now what we're seeing is we'd be measuring that much noise. So in this region down here, when we're actually trying to measure the DC thing, basically our entire signal was covered in noise. Whereas now, if you look at this case here, we're seeing our signal clear, and then we've got this much less noise in the background. And so we're actually getting a better measurement by finding a frequency range in which the measurement is going to work better. So this is what's going on with phase sensitive detection. And if we increase the amount of time we average for, we reduce the bandwidth, and therefore we narrow down this blue rectangle here, and we include less and less noise and retain just the bit of the signal we're actually interested in. So this is really the power of phase sensitive detection. And you'll find phase sensitive detection is being used in many, many experimental situations. So it's not even just where you've got a lock-in amplifier there, obviously there, but in many cases you'll find that there is in fact a phase sensitive detection process hidden away in the background there, in many, many different types of instruments. And so understanding the effect of changing the frequency, of changing the amount of time you average the signals for, gets you to understand why certain combinations of things are going to work well. The flip side of these sorts of things is, of course, you can't just reduce your bandwidth through a measurement indefinitely, because that's the same thing as saying your measurement is going to take longer. And then you have to start thinking about things, well, okay, this is a noise spectrum, but if I took forever to go and do my measurement, is this noise spectrum going to stay the same all the time? And so what you might find is that, for example, over time, your noise spectrum changes, and if you take too long to do the measurement, in fact, you're doing worse than if you accepted a slightly bigger bandwidth and a bit more white noise in your measurement, but overall it gets you a better measurement. And of course, the other constraint is you can't wait forever to go and do your measurements, because you know, reality kicks in and there are other people who need to go and use a measurement kit. You need to get your experiment. So the next approach we're going to take to trying to improve our measurements is to think about ways in which we can increase the resolution of a measurement, to get a sensitive measurement of a small change in the signal. So resolution can be considered as the way as what happens when you divide the maximum range by the number of discrete number of different levels over which you can do that measurement. So for example, if you have a 10-volt range, plus or minus 10 volts, and you've got 2 to the power 16 levels, so a 16-bit digitization, then that gives you a resolution of about 0.3 millivolts. So you can tell the difference between two signals which are 0.3 millivolts apart or more. If you want to try and improve that, to go and measure a smaller change in voltage, and you don't want to go and have to increase the absolute number of digitization levels, so in other words, not to have a more expensive digitization process, then you have to find a way of reducing the maximum range of the signal. And then you can keep the same number of discrete levels, but get an improved resolution. So this basically ends up saying that it's much easier to measure a small change from zero than a small change from a large signal, because if you have a small change from zero, you can reduce that maximum range you're trying to measure over. So null detection schemes are a way of trying to implement that to actually let you try and measure a small change from zero rather than a small change from a large signal. And I'll give you a couple of examples of ways in which that might be done. So our first example for a null detection circuit is to use a scheme called a Wheatstone bridge. So this is a very simple resistor network, such as you might have analysed in Physics 1. So it basically consists of a diamond of resistors. Okay, so we have 4 resistors like that, and 2 of them are our sensor. So this is using 2 sensors hooked up, and we have 2 reference resistors. And what we're doing in this scheme is we're measuring across the middle of the diamond here from A to B. Now, if we set things up so that our reference resistor is approximately the same as the sensor resistor, then it should be fairly clear, I hope, that the voltage here is going to be about half of this supply voltage we're applying to the network. And the voltage at this point here is also going to be about half of that. And therefore, the voltage difference from A to B is going to be very, very near zero. And then when we go and change the resistance of the resistor sensor here and here, what's going to happen is that if they say these resistors have reduced their resistance, then this voltage here is going to drop, and this voltage here is going to rise, and we're going to get a difference from A to B. So we can actually work out how it's going to work. So we can write down the voltage at A is the sense voltage times the sense resistor over the sum of the two resistors. And the voltage at B is going to be given by the supply voltage times the resistance of the reference resistor over the sum, like so. And the voltage we measure, delta V, is therefore going to be supply voltage R sense minus R ref over R sense plus R ref. And so now you can see the effect. If we go and change, say if we reduce the resistance here, this top part is going to become positive away from zero, and this part here will decrease slightly, but not very much. And so we start getting a voltage we can measure. So it might be instructive to actually work out the sensitivity of this device. So what we can do is we can calculate the differential change of that voltage with respect to the change in the resistance of the sensor. So that is going to be V sense, and we're just going to use standard differentiation rules, whoops, squared, and I'm going to want on the top here minus R sense plus R ref, and we're going to have minus R sense minus R ref. And so when we do this, we're going to find that we're going to end up cancelling out terms on the top there. So we're going to have, so it's going to be minus, oops, minus 2 R sense, and then the R references cancel out over R sense plus R ref squared. And if we take the case where we're trying to make the thing so that the resistance of the sensor and resistance of the reference are approximately equal, then that ends up being approximately, oops, I missed out the vol Vs there, minus Vs over 2 RF, or R sense, doesn't really matter which way around you do it. Okay, so that's telling us how we can change the sensitivity. We can actually do the same analysis if you have just a single potential divider, so just one arm of this circuit, and you'd find that your sensitivity again was about half, was the same number. If you just had the sensor resistor, then the sensitivity would be double that. Now, okay, that sounds like we've just halved the sensitivity. So what good have we done? Well, what good we've done is we've made that the signal when we're just sitting there idle and in the idle state is 0 rather than the voltage supply level of the signal. So what's going on then is we are okay, not necessarily improving our sensitivity, but we are improving the point at which we're starting. So we're measuring away from 0, And so we're able to get a better resolution. So without changing the sensors particularly, we're able to improve the resolution of our measurement for a certain amount of digitization. And so that gives us an advantage in terms of the actual data we collect. Okay, so let's think about another example. So one of the measurements we quite often do if we're using an atomic force microscope is we need to sense the position of the of whether the tip is. So the way an atomic force microscope works is you have a cantilever like that, and it's got a sharp tip on it, and that's traveling over the surface. And what you're trying to do is detect the movement of this cantilever up and down like this. So what we arrange for is we arrange for a laser to be reflected off that tip, like so. So as this tip flexes, that laser will move up and down in an arc like that. So it's coming in like that. And then we have to try and somehow measure the position of that laser. So what we do is we can use a photodiode. So a photodiode will give us a current when there is when light is falling on it, and not when it's not. But in order to measure that, it's kind of got a large background signal, and we want to measure exactly where it's going. So rather than just using one photodiode, we arrange to have 4 of them. So we have a sensor that looks like that, and it's divided up into 4 photodiodes, A, B, C, D. And so we fix it so that when the cantilever is in a neutral position, that laser illuminates those 4 photodiodes equally. And then what we do is we look at the signal from A minus the signal from, plus the signal from B minus the signal from C plus the signal from D. So if the laser is illuminating exactly evenly vertically, then the total signal on A and B will be the same as the total signal on C and D, and so that will give us a 0. Then when the cantilever moves down, what you see is that the laser spot would hit more onto C and D, so this signal would get bigger, so the overall signal we're looking at will go negative, and likewise when the cantilever moves up and light falls more on A and B, the signal goes positive. And then what we do is we control to send this signal back into a feedback loop to adjust the position of the cantilever to try and keep it steady. And you can do the same laterally. So if the cantilever twists and you look at the signal in A plus the signal in C minus the signal in B plus the signal in D, then again you can see as the cantilever twists and the laser spots move more to the A and C side and away from the B and D, you're going to get a positive signal. When it goes the other way, you're going to get a negative signal. And again, you can map out what's going on. So although the signals of these things each may be aren't changing very much, and they're starting from quite a large background level, by looking at the differences between these signals, you've got this null detection scheme going on, and you're able to go and get a better measurement, more sensitive measurement. So it's always worth, when you're trying to work out how to get a good measurement and you have a sensor which is giving you a large background signal, to try and set up some kind of null detection routine in order to go and cancel out the unwanted background signal. So typically, as I say, using potential dividers or subtract. So the final class of general experimental techniques we want to go and use to try and improve signals is to go back to our trick of using stroboscopic measurements, but there's a particular case of this, which is generally called a pump probe experiment. So this is very useful when you want to measure some very, very fast response to a stimulus, but you also know that it's reproducible. So that every time you go and hit it with a stimulus, the thing's going to respond in the same way. And this is a particularly common technique in optics experiments, but it's something you can use more generally as well. So again, what it requires is that your response to the stimulus is repeatable, and as with other stroboscopic measurements, that you can measure the same thing at a very precise time and with a very small amount of jitter. So I'll show you some sort of general kind of ways in which these things are often set up. So the secret of a pump probe experiment is to be able to have some mechanism which we can apply a stimulus and then to do a measurement sometime later. As I said, the classic way of doing this is to look at optics type experiments. So we might, for example, imagine that we had a setup where we've got a laser, and then we're going to take that laser beam and we send it into something that splits that beam into half, or it splits it into two parts. And so we have, by the way you can actually do this, I've drawn this as a square with a line through it. Actually what it is literally a prism of glass like that, another prism of glass like that. And because there's a refractive index mismatch between the glass and the air gap, what happens is that as the light comes in, it will get, some part of it will get reflected and some part of it will pass through. And by arranging the refractive index of this joint carefully, then you can, in fact, you can do it without the air gap. You can just do it by having two different bits of glass with slightly different refractive indices. You can set it up so that you get part of your light coming off this way and part of your light going through. And by controlling the mismatch between the two refractive indices, you can control what fraction of the light comes down and what fraction of the light goes through. So in this particular example, we'll say send 10% of our light that way, and therefore 90% this way. Okay, so what we do then is we then arrange for this part of our light to come, and we'll have it strike our sample there. So that's our pump. So this is a big powerful burst of light which is hitting our sample. And what we do is we then send this part of the light, and we send it through maybe perhaps like a delay line. So that's where we arrange to have two mirrors. Arranged like that, but we can also move the position of this mirror backwards and forwards. And we have the light bounce backwards and forwards like that. And eventually it comes out of the delay line. And then we can just arrange again to have mirrors. Okay, so we're making our sample something that's transparent. And our probe pulse comes through like that. And the final thing we need to go and do is we need to have some kind of pulsing mechanism. So this is a pulsed laser. So one of the things you can make is, and we'll talk a little bit about this in the optics sources, you can make lasers which turn on and off very, very quickly and send you a femtosecond long or a nanosecond long pulse of light. So in this sort of setup, what we're doing now, I suppose we need to send this to some kind of sensor. So we have some sort of sensor over here. So the scheme we're doing is we're taking the same pulse of light, we're splitting it up, we're bouncing it back and forth over a delay line, and then the powerful pulse of light goes and hits our sample. And by changing this delay line, you change the optical path length that this light has to go through, and therefore you change its time it arrives relative to the pulse you hit it with. And so that gives you this stroboscopic type of measurement. By changing this delay line, we change the relative timing between the pulse of light that's pumping it and the bit of light that's probing it. And you can get far more complicated sort of setups with more complicated geometries. You can do things where maybe these laser pulses, this pulse is in fact not directly hitting the sample, but maybe it's triggering some, I don't know, terahertz generation or something like that on your sample, or it's somehow triggering an electrical pulse onto your sample. The concepts are all basically the same, is that you arrange that you have one stimulus which you split into two parts. You arrange for one of those parts to be delayed, and it arrives at your sample sometime after the stimulus, and that's the thing you're using to then probe and measure with. So this is a a kind of approach of doing a measurement that's really very, very common in optics type experiments. So that's what we mean when we say a pump probe type of measurement.